My name is Nikos Panankopoulos, and I will start by providing a short introduction to the project. FleX-RAY is a 3-year EU-funded project that started in 2020 and consists of a consortium of 5 partners: TWI Hellas from Greece, Fraunhofer Heinrich Hertz Institute from Germany, Optoelectronica from Romania, RISE Research Institutes of Sweden, and the University of Sheffield. The main objective of the project is the development of an inherently flexible radiographic imaging detector. Aiming to replicate the ease of use and versatility of radiographic film, our project aims to bring together the benefits of analog radiography's detector flexibility and digital radiography speed and resolution. Modern detectors, due to their reliance on solid-state materials, are not flexible, or at least not to a high extent. In the past couple of years, though, we have seen some products emerge that can be curved to some extent. The core component of our detector are scintillating optical fibers. These are special fibers that convert high-energy particles, such as X-rays, gamma rays, cosmic particles, and others, into visible light that can then be captured by photodiodes. By constructing a multi-layer matrix of scintillating fibers, the position of photons impacting the matrix can be detected by recording their travel through the different layers. This concept is presented in the system diagram. The scintillating fibers are arranged in the form of 2 matrices, one on top of the other and at right angles to each other. The area that intersects fibers between the 2 layers is the equivalent of a pixel in this type of detector. Each end of each fiber is terminated to a photon counting sensor, or SIPM, which measures the intensity of light produced by scintillation. The signal generated by each SIPM is then transferred to high-speed processing electronics. An ultra-thin 3D shape sensor is also integrated in the detector and is used to calculate the current shape of the scintillating fiber matrix. This information can be used by the image reconstruction algorithm to correct for image distortion due to curvature. The output of this sensor is also fed to the processing electronics, which convert this information into an image. This is a novel concept with a technology readiness level, or TRL, of 1 at the start of the project. A number of challenges had to be overcome to bring this concept to reality. One of them is the fact that commercial off-the-shelf scintillating fibers have large diameters, therefore leading to large pixel size and low resolution. This raised the need to manufacture custom-made scintillating fibers, which can bring the achievable resolution to compete with state-of-the-art digital detectors. Another challenge is that large curvatures may add distortion to the converted image, thus raising the need for self-shape detection and image correction. Digital radiography also deals with large amounts of data that contain noise that has to be filtered out for a useful image to be produced. The entire process of photon detection, shape sensing, and image reconstruction has to be carried out in real time, raising the need for the development of cutting-edge electronic hardware. Finally, to reduce exposure time and lower the effect of noise, high-sensitivity sensors and high-quality optical couplings have to be developed. A detector of this kind would present a number of advantages in comparison to current state-of-the-art detectors. Electronics could be separate and distant from the detector thanks to the low attenuation of optical fibers. This would lead to a more portable and lower-cost detector. Inspection time could be reduced, since a single exposure would be sufficient to inspect a complex geometry that with today's technology would require multiple exposures from different angles. Self-shape sensing would allow correction of an image taking into account an object's geometry, thus reducing distortion. Another benefit of a highly flexible detector would be its ability to be wrapped and then unwrapped, allowing it to be inserted into confined spaces. Such a detector could also be used to capture cosmic particles, which is a method used in archaeological exploration.
Hello everyone, welcome. My name is Nazila Safariyast. I present a summary of our work in this project. My colleagues and I work in the Fiber Optics and Photonics unit of RISE Institute located in Kista, Sweden. As Nikos explained, the core component of the detector in this project is scintillating optical fibers. Glass optical fiber gives more flexibility than plastic fiber with higher resolution due to its smaller size. The scintillating optical glass fiber consists of hollow core fibers or capillaries filled with scintillating liquids, then connected to multimode fiber and recoated with low-index coating material. When X-rays hit the section of the component filled with the liquid or the active part of the component, the X-ray is absorbed by the scintillating liquid and its energy is converted to scintillating signal in visible range. The scintillating signal is propagated through the optical fiber and the liquids and reach the SIPM's sensors or photon counting sensors. Then the signal will be measured. We are flexible in choosing different types and size of optical fibers to make scintillating components, since at RAYS we make different microstructured solid core optical fibers, hollow core fibers, and capillaries with different diameters. These microstructured glass optical fibers can be connected to other standard optical fibers like multimode fiber by conventional methods like fusion splicing that reduce the optical losses. We can select different scintillating liquids like organic liquid or inorganic liquids to make our component. We fabricated several designs of silica-based scintillating optical components. It can be an easy design using a 15-micron capillary filling with liquid and splicing to multimode fibers on both sides of the capillary, or we can use two capillaries with different size of diameters and make the component. Or it can be a complicated design like the third one in the picture, using 15-micron capillary, two-hole fiber, and housing capillary. We can design specific components to achieve desired scintillating parameters depending on the application, like light trapping efficiency, scintillating wavelengths, and so on. On the right side, you can see the image of fabricated scintillating silica components, which made at RAYS. We evaluated our silica-based scintillating components with the setup shown in the picture. We used UV light to excite scintillating liquid. The multimode fiber is connected to a spectrometer by a bare fiber connector. The spectrometer detects the scintillating signal and gives the signal spectrum. On the right side, you can see examples of these scintillating signals of two components filled with two different scintillating liquids, BC505 and quantum dot-based liquid. Finally, we have done an actual X-ray test. In this test, we compared our silica-based component and a plastic scintillating fiber using this setup to expose the fibers to the X-ray source. As I mentioned before, plastic fiber has a bigger diameter than the glass fiber, in this case around 20 times bigger. Therefore, the scintillating results are different. As you can see in the graph, the scintillating of a glass component made at RAYS is at least 3 times bigger than the plastic fiber scintillating. Therefore, these good results motivated us to make a detector based on the glass optical fibers. We made one and hope that the results of our detector together with other partners' results in this project open new doors to create flexible X-ray detectors for future industrial and research imaging applications. Thank you so much.
The detection process starts as soon as a high-energy particle, such as an X-ray photon, travels through the detector. Visible light photons are then generated within the fibers as a result of scintillation. These visible light photons then travel down the length of the fibers, where they are detected by highly sensitive photodiodes. By knowing which photodiodes were stimulated on the upper and lower layers, we can pinpoint the position on the detector that each high-energy particle traveled through. By counting the number of photons impacting the different sections of the matrix, we can estimate the intensity or flux of the X-ray beam and thus generate an X-ray image of an object. In order to detect the light produced by the scintillation phenomenon, we use a specialized device called silicon photomultiplier, or SIPM. The silicon photomultiplier is a device that allows the measurement of light levels down to single photons. Each SIPM consists of hundreds or thousands of photon-sensitive microcells, which are 10 times smaller than the width of a human hair. Silicon photomultipliers come in a range of sizes and characteristics suitable for different applications. The output of the silicon photomultiplier is an electrical pulse. This signal has to be amplified by a preamplifier before it can be further processed. Next, the signal is provided as input to a comparator that checks whether its amplitude is over a predetermined threshold. This threshold is used to reject unwanted signals which appear as noise. Next, the useful information of the signal is extracted by the time-to-digital converter, which calculates its length and timestamps its time of arrival. These electronic circuit blocks comprise a channel. An SIPM is connected to each channel. This collection of electronic channels form the analog front end, or AFE, of the system. The data output from the AFE is fed to an FPGA, which performs digital signal processing of the signals and then sends the results to a computer that runs the image reconstruction algorithm. The entire process described above lasts for only 25 millionths of a second. The time resolution of the AFE electronics, which is the smallest time difference that can be resolved between channels, is a few tenths of billionths of a second. On this slide, one of the SIPM printed circuit boards of the FleX-RAY proof-of-concept prototype is presented. This board features 8 SIPMs, each to be connected on the end of a scintillating fiber. 4 such boards are used in the prototype. Each board is mounted on an active cooling element in heatsink and is cooled to sub-zero temperatures as low as -20 degrees Celsius. This helps to reduce the amount of electrical noise, known as dark current rate. The analog front-end and FPGA electronics are integrated into a single printed circuit board. This board from Wirok allows for simultaneous connection of up to 32 photon-counting SIPMs. This image on the right shows the complete proof-of-concept prototype while undergoing functional testing. Some results from this testing will be shown in a later presentation today.
Hi, my name is Yannis. I'm with Fraunhofer HHI, and I want to present to you the 3D shape sensing that we've done in the FleX-RAY project. So as you've heard, our X-ray detector is flexible, and that means that in contrast to conventional X-ray detectors, we end up with a distorted X-ray image. And this is not what we want. What we want is the correct X-ray image, or a corrected X-ray image. And our task is to figure out how to get there. And we do this by getting the 3D information of the X-ray detector by placing a 3D shape sensor on top of the X-ray detector. So the 3D shape sensor essentially consists of lots of curvature sensors placed all around it in both X and Y direction. And for this we use ultra-thin glass, which you may know from your smartphone displays, especially those new flip phones. And we use femtosecond lasers to integrate into the glass waveguides and Bragg gratings. Bragg gratings essentially act as curvature sensors, and I've indicated one of those here with some white lines. So the ultra-thin glass is about 1/10 of a millimeter thick, about the thickness of a hair, of a human hair. And it's flexible, so it can adapt to the X-ray detector's shape. It doesn't take any damage from X-rays, in contrast to electronical sensors. And it gives precise and repeatable measurements because everything is integrated into a single material, unlike compound sensors, which other optical methods use. And you might interject, well, if this is the material that is in my smartphone, then I know this shatters. And while we do try our best, it doesn't shatter. It happened before, yeah. So let's instead talk about the sensing principle here. So we start with a light source that gives out a broad input signal, And when this hits our curvature sensor, the Bragg grating, it reflects a narrow part of it, a narrow signal, and we can then detect that with the spectrometer. Now, the good thing is, what we use is that when the sensor is stretched, the reflected signal moves to the right in the spectrum, and if it contracts, then it moves to the left. So we can use this to distinguish bending in two different directions, and also to know the amount of curvature, the amount of bending. And this is important because, let's say we have a flat sensor, a flat shape, then the Bragg grating reflects its wavelength. And if you bend it into the one direction, the Bragg grating would be compressed. That means the signal moves to the left. If it is bent in the other direction, the curvature sensor is stretched and the wavelength it reflects moves to the right. Now, how do we end up at the 3D map at the end? So we take the curvature information from 4 curvature sensors in a row to form a 2D curve. And if we do that along all the lines that we have in the 3D sensor, we end up with the 3D map. So here you can see how the 3D shape sensor is placed in our testing setup. And on the right, you can see the 3D shape recalculation. So as the sensor is moved, the 3D map is updated in real time. And this is important because we also want to be able to calculate the correct X-ray image in real time. So to integrate the sensor into the whole system, to the FleX-RAY system, we placed the glass between 2 plastic sheets so it can still move around smoothly, there's not too much friction, and then cover all that in silicone to give it some kind of stable housing and also to be able to connect it to the X-ray detector, which is also in silicone. So to summarize, the problem we were faced with is the distorted image, and we add a 3D shape sensor to be able to come up with the corrected image at the end. Thank you.
Hello, my name is Scott Wilbur, and I'm going to be talking to you about the FleX-RAY image reconstruction algorithms. Here's the concept image of FleX-RAY that you've seen before. And unlike in a detector that has individual pixels or a sheet of photographic film, we can't simply integrate each point to get an image out. We are only reading out the information along the edges with silicon photomultipliers, and therefore we need specialized algorithms to translate that into a proper image. So this is essentially a photon counting detector. We need to reconstruct the position of each individual X-ray hit. There are 2 scenarios we need to look at. One is when an X-ray comes in and gets absorbed in a single fiber and scintillates in all directions. And the other is when an X-ray comes in and scintillates in both an X fiber and a Y fiber simultaneously. We have algorithms to look at both of these detections, and they're useful in different cases. So the first scenario is one-dimensional reconstruction, when an X-ray only scintillates in a single fiber. This is much more common with low-energy sources, such as an X-ray tube. So the light from the single scintillation in the fiber will will travel in both directions toward both ends of the fiber, and will arrive at the photomultipliers at different times, T1 and T2. By taking the difference between those times and the speed of light within the fiber, we can find the position of the hit somewhere in the fiber. This position is significantly blurred by the uncertainty in timing, both from the scintillation characteristics of the fiber and the time resolution of the photomultipliers, as you can see in this simulation on the left. However, because that blur is only along the fibers, so horizontally and vertically, and never diagonally, this can be vastly improved by post-processing. By using a custom deconvolution algorithm, we can get much closer to the original image than that blurred one. The second case is two-dimensional reconstruction, which is when the X-ray scintillates in 2 fibers at a time. This is much more common with high-energy sources, like radioactive sources such as iridium-192. If an X-ray lights up 2 fibers at once, it just pinpoints the location right away. This can get much better images than the 1D reconstruction, even without the post-processing, as you can see in this simulation on the left, but only if the source is suitable, if it's a sufficiently high energy source, and if you don't run into the problem that I'm about to describe. If the source is too intense, then overlapping detections can create false hits. For example, if we get a detection here and here at the same time, that looks just like a detection here and here, by which fibers light up. We may need to slightly decrease the power of certain sources by adding more shielding in front of it to get a better image, depending on the sources that are being used. Here we have a simulation of a future detector using both of these methods. The object we're looking at is a 5 centimeter diameter pipe with a small corroded area in it and a very thin crack. By shooting some X-rays through this, I'm specifically using a simulated iridium-192 source for this. We can get an image with the one-dimensional reconstruction here, and an image with the two-dimensional reconstruction here. The two-dimensional image is of course much better. You get a better resolution of the corroded area, and you can actually see the crack, which is very difficult even with the post-processed one-dimensional reconstruction. So the two-dimensional reconstruction, it requires higher energies, such as an iridium source, and it requires lower intensities to avoid the overlapping detections. But if you have a source and an application that satisfies those requirements, the two-dimensional reconstruction can give you a much better final image.
An early demonstrator detector of 16 plastic scintillating fibers was developed to test the concept of flexibility. This prototype consists of 2 layers of 8 fibers integrated in silicone. A potting apparatus was also designed, and a number of compounds were evaluated for the strength and flexibility. A mock-up of the proof-of-concept prototype is shown on this image on the right, with the detector located in the middle of the structure. The actual proof-of-concept prototype is shown in this slide in preparation for testing. The detector and photon-counting electronics are situated on the left of the image, with the AFV and FPGA electronics that receive and process the signals on the right. Initial testing of this prototype was carried out using a strontium-90 radioisotope. This element is a silver-looking metal that is produced by nuclear fission and emits beta radiation while it decays. Since it only emits beta radiation with a short range, it is an ideal element for testing our detector, as it can trigger scintillation but it cannot penetrate thin layers of most materials. It therefore does not pose a risk to health if handled properly. A number of initial tests were carried out using strontium-90 as a simulated X-ray source. During these tests, we evaluated the performance of the photon-counting electronics and image reconstruction algorithm by placing simple geometrical objects in front of the detector. In this image, the result from placing a steel washer in the middle of the detector is shown. Next, the washer is moved to the bottom edge of the detector. In the next image, the washer is moved to the top right edge of the detector. In the final image, a copper terminal post is placed in the middle of the detector. These results show that the photon counting and AFE electronics has a sufficiently good time and signal amplitude resolution to allow for image reconstruction of a simple geometry. Follow-up tests using an X-ray source were carried out. However, these results are pending processing and internal review, so will be included in a future project publication. Throughout the trials we have carried out so far, we were able to conclude that the technology can be used to produce radiographic images of objects with simple geometries and varying thicknesses. Based on our findings, we are now evaluating potential end-use applications such as thick specimen testing using gamma rays, container good scanning at customs checkpoints, creating a Copton camera for proton emission therapy, and similar. Such an application would serve as a target to aim for on a follow-up project. Thank you for attending this webinar. We will be glad to hear how the FleX-RAY technology could potentially help you solve challenges in your own field of work.